right, Ethan. Sorry about my little boneheaded move today where I didn't know what the heck was going on. I, I wish I could say I'm surprised, but I'm not. I do things like that way more often than I should. All right, so section 3.5. I love me some section 3.5. So, first, we're going to talk about what a polygon is. Okay, so it's, I think, oh, hang on, I'm sitting here in front of a computer. I don't need to think, I can look it up. I think it's Greek. Let's see. Etymology of polygon. Oh, I'm so good. It's Greek. It's from the Greek polygonon, maybe? That means many angles or many angled, whichever way. The thing I'm looking at right now says many angled, but the geometry book said many angles. Close enough. So each polygon is formed by coplanar segments. Okay, so everything has to be in the same plane. We call those the sides, so that each endpoint intersects exactly two other segments, one at each endpoint, and that no two segments with a common endpoint are collinear. So, let's talk about that one first. Those two segments wouldn't be considered two different sides of a polygon if all the points in those two segments are collinear. That'd be silly. That's just one segment. So that's what that's talking about. That's a no. Oh, actually, before you start drawing that, just listen to me say this, because that space right here, I need some room for. And then each endpoint intersects exactly two other segments, one at each endpoint. So that's basically saying, okay, we could have this, but we won't have a third thing coming from that same endpoint. All right. So the polygons are the shapes that you're probably most familiar with. We'll get to all the names of them. But there's 4 characteristics of polygons. Okay, so number 1, they're flat. So you won't have anything three-dimensional. And that's taken care of up here by saying they're coplanar. They're closed. All right, so what that is, I'm just going to show you an example. That is closed. That's not closed because there's a way inside. So all of the endpoints have to connect to another endpoint. Let's see. They're simple, and that's kind of a weird. These are the 4 words that the first book I actually. Let me think. Was that the book I learned geometry from? Yes. So the textbook series that I actually learned geometry from, and the first time I ever taught this, was out of that same textbook. And these are the 4 terms that they associate with polygons, and they've just kind of stuck. And I think that these 4 things will take care of you. So this, not simple. Not a polygon. Not a polygon. And then the last one is that all sides are straight. So if you've got a shape like this with a semicircle on the end, not a polygon. Okay. Where are these in my notes? I was going to say, let's just go ahead and we're going to come back to this. But going over to the next page where it says polygons are classified according to the number of sides they have, just to make sure that, you know what I'm talking about. If it has 3 sides, a 3-sided polygon, that's a triangle. A 4-sided polygon, we call those quadrilaterals. A 5-sided polygon, you got it, it's a pentagon. A 6-sided polygon is a hexagon. All right, 7 you may not know, although I do know you, and you probably do know. You'll see it one of 2 ways. People either call them heptagons or septagons. Okay, 8 sides, is an octagon. 9 sides, I've seen 2 different ways of calling those. I usually call them nonagons, but I've also heard them called enneagons. A 10-sided polygon is a decagon. An 11-sided, I always call them undecagons, but some people call them hendecagons. That's an H. Doesn't really look like an H. Hendecagon. And a 12-sided is called a dodecagon. Now, if you really like how to name these, there's actually official names for all of them past 12 sides, so 13 sided and on. I have never taken the time to learn that. I've read through it a couple times, and it is interesting. So you're more than welcome to look that up. But pretty much everybody who doesn't have unlimited brain power to memorize things like that, they stop at 12, giving them a name. And anything after that, it's just an N gone. So, like, if it had 44 sides, we'd say that's a 44 gone. And don't say 44 a gone. Like, don't put the letter A in there. It's just 44 gone. Okay, so that's the names of them. But coming back up here, let's talk about convex and non-convex, which I was doing the notes like this non-convex. The book that you're learning out of calls them non-convex. Most people call them concave if they're non-convex. So I guess we should probably talk about what convex means first. So a convex polygon is a polygon such that no line containing a side of the polygon contains a point in the interior of the polygon. Okay, so that's, let's say we just draw any convex polygon, and we say no line containing a side of the polygon contains a point in the interior. So that's basically, if you pick any side and you extend it and you look at the side, that line, that none of the points on that line will be inside the polygon. Like you could put a line here. None of those points are inside the polygon. Now that's the definition this textbook had. I like a different definition better. If something is convex, that means I can pick any two interior points I want, connect them with a line segment, and I did not connect them with a line segment. And no part of that line segment will be either on the polygon itself or on the exterior, or I guess on the exterior, outside the polygon. Okay? So if a polygon is not a convex polygon, then we say it's a concave or a non-convex polygon. And that would be, like, to go along with the definition that your book has, that would be like, okay, we can take a side, extend that side, and some of those points will be on the inside, the interior of the polygon. Again, the definition I like better to make it concave means that there are at least 2 points that I could take on the interior of that polygon that I could connect with a line segment, and at some point in time, some of the points on that line segment would be outside the polygon, not a convex polygon. Most people, I'll be honest, most people remember that there's a cave. So if it's got like, it dents back in on itself and forms a cave-like shape, we'll say they're concave polygons. Now this is important because this is the kind of question that you would ask me. This was written in the textbook. So whenever our book refers to polygon, the word polygon, the authors mean a convex polygon. However, standardized test writers and other authors do not mean that. So most of the time, I'm going to say the word convex so that you know it. If I ever don't put the word convex, assume that it's, well, should we say that? Because on an always, sometimes, never, I don't want you to assume that. Okay, so let's just say this then. When you're in the textbook working problems, if they don't say it's convex, assume it's convex. Any other time, do not assume it. And so that way, if I've messed up and not given you enough information, then we'll talk about it and you'll be on the lookout for those things. Because, like, you don't want to start assuming that. I don't think that's a good plan. So yes, let's just say this applies only when you're working problems out of the book. Okay. So we got our names. The terms that we applied to triangles, vertex, exterior angle, they also apply to polygons. So let's say we take just some random pentagon. Okay, so a pentagon has 5 vertices. So like this is, and we would name this, let me get them labeled up. So you say this is pentagon A, B, C, D, E. But you could also call it pentagon A, E, D, C, B. Or you could call it pentagon C, D, E, A, B. All it is, you have to pick a point, one of the vertices, and then you work your way around either clockwise or counterclockwise, and nobody cares until you get to the last vertex. So that's how you name these things. So we got our vertices. An exterior angle, just like on a triangle, is you take a side and you extend it, and then it's that angle right there. So this is your exterior angle. that is formed by the extension of that one side and one of the adjacent sides. Okay, so like we could say right here, C is a vertex. And then angle C, we'll have to name something out here. I already have an E. Let's do F. So angle CDF is an exterior angle of pentagon ABCDE. And you really don't even have to say the word pentagon. You can say it's just an exterior angle of ABCDE. Okay. So when referring to the polygon, all right. Can you tell it's been a while since I did these notes? I haven't taught this class since 2021. So when referring to a polygon, we list its vertices, consecutive vertices in order. So we'd say pentagon. Let's just pick a random one, and we'll go clockwise. So I could call it pentagon EDCBA, or I could call it pentagon. Let's pick a different one. Let's start at B and go counterclockwise. Oh, I'm still going clockwise. What am I talking about? Let's start at B and go counterclockwise. So BCDEA. All right. And then a segment that joins two non-consecutive vertices. So I'm going to go back and erase this. So consecutive vertices would be the ones that are right beside each other. Those are consecutive vertices. If you connect those with a segment, that's a side of the polygon. If you take two vertices that are non-consecutive and you connect those, these are known as diagonals of a polygon. Okay? And in this picture, the diagonals are represented with dashes. That doesn't mean people always do that. All right, so here's the big stuff. To find the sum of the measures of the interior angles of now this is only of a convex polygon. Draw all the diagonals from, we're just going to prove why it works. We're going to draw all the diagonals from just one vertex, and we're going to divide these polygons into triangles. So we'll just start out. Interior angles of a triangle. You know that's 180 degrees. So let's take a quadrilateral. So we're going to pick a corner, and we're going to draw every diagonal that we can. So there's just the one. But what you've done is you've divvied it up into two triangles. Okay? And then there's 180 degrees in this triangle. There's 180 degrees in this triangle, which means there's 360 total degrees because it's two of those triangles. Here is one of those triangles. Now, if you're wondering like what I'm talking about, this angle right here added to this angle, added to this angle. So like those three angles add up to 180 degrees. And then this angle, and that angle adds up to 180 degrees. But like when you combine those two together, you get this big angle in the quadrilateral. Same thing over here. You get that big angle. So those six angles add up to 360 degrees, which means those four angles in the big shape add up to 360 degrees. All right? So let's do a pentagon. And again, we're just going to pick a corner and draw every diagonal that we can. And then we've divided into three triangles. So there's 180 degrees in this one, and 180 degrees in this one, and 180 degrees in this one, which means I've got three of the 180s, which gives me a total of 540 degrees. If I do a hexagon, 2, 3, 4, 5, 6, pick a corner, draw in every diagonal I can, I've created four triangles. So four of those 180 degrees at a time, 0, 32, okay, there's 720 degrees. All right, what if there were 10 sides? And I'm not going to draw it. But what's happening? So right here, when you had 6 sides, there's 6 vertices, right? So if you're trying to, like, you pick your vertex that you want, and you can't connect that vertex to the one beside it or this one, because those are the sides of the polygons, but it does leave you 1, 2, 3 of the diagonals that you can draw. But by drawing those 3 diagonals, you actually create 4 triangles. So over here we had 5 sides. We created 3 triangles. Here we had 4 sides. We created 2 triangles. When we had just 3 sides, we only had 1 triangle. So I think you see what's going on. The number of sides, there's 2 less than that number of triangles. So if there's 10 sides, then I would have 8 of those triangles created. And what is that? 0, 64, carry the 6, 1440. So if there were n sides, so let's say it's an n-gon. I guess we should probably call it the whole thing. So take an n-gon, then however many sides there are, I'd take 2 away from it, and then I'd multiply by 180 degrees, and then that's the sum of the interior angles, because if there's n sides, that means I can make n minus 2 triangles from it. So that is why that works. Okay? So what if they just gave you this? You have a dodecagon. Oops, probably helped to spell it right. Dodecagon. And somebody said, what is the sum, here's our question, of the interior angles? Of this dodecagon. Now, I'll be honest with you. The interior angles of a convex polygon are also, wait, hang on. Is it this one or the exterior? I never do the ones with the convex. Yeah. I'm looking it up again. Sum of interior angles of a no, let's do concave polygon. I think it's the same formula, but I don't remember. It is. So that's why it's okay if we don't. And I gotta remember why that works. Oh, because it's the same reason. Hang on. I was thinking, like if I draw a concave one, then if I pick a corner right there, like this still adds up to 180. This angle, still 180. This angle, still 180. This, and this, still 180. And if you put all like, I want that angle, this big angle, this big angle, this big angle, this big angle, and this big angle that went past 180 degrees, that's still the interior angles. So on these, it doesn't matter if I say the word concave or convex. It's just of a polygon. This is the formula. So if they said, what's the sum of the interior angles? Then you'd say, oh, well, there's 12 sides. That's going to make 2 triangles, or 10 triangles. There's 180 degrees in a triangle. That means I've got 1,800 degrees total. And that's it. That's all you do. All right. Ooh. I wonder if I can do this. Ugh. Okay, I'm going to stop the video. So this video will be in 2 parts, but I'm going to see if I can look up online the video that I want to show you, because it's pretty cool. And I've been talking for a while already, so this is probably a good one to split into 2.